Hi, I'm Luke BERNDT from IQT Labs, and I'm going to give a quick walkthrough on sort of the journey we had on working with visual wake words and some of the lessons we learned along the way. I came at this really from a practitioner who's been familiar with embedded systems, really high-grade embedded systems, and picked up some useful real-world tips on how to work with machine learning models in an embedded environment. So the good news is, ML vision sensors are here. I think in our next talk from Mark, we'll learn a bit more about the HiMax board. But really, these are low-cost, low-power devices powered by a microcontroller. And with these, the camera there, it's not to take pictures of cats and give you cat photos. It's really to help answer questions like, is there a cat in the room? So these, they don't take photos. They really are about providing an answer. The visual wake word data set has sort of emerged as, the initial way to start training a model for doing visual tasks in tinyML. It trains a binary image classifier using images from the Coco Data Set, and it ends up training a model that will let you know, is this object in an image or not? It does this by going through all of the images in the Coco Data Set and sorting out, based upon the labels, is there this image object in the image or not? And it will also sort through and take a look at the bounding box of the image too. So in many cases, the actual input image is very small, and if the actual object, it's a distant cat, appears not to even be inside the image when you train, it will remove those too. So a really good resource for getting started. And so it might lead to the question of what is the Coco Data Set? It stands for Common Objects in Context. And it's made up of non-iconic images from Flickr of different objects. In the upper right-hand corner, we have some examples of iconic images. And this is just where the object is, front and center. There's not much around it. Versus down below is more the target for the Coco Data Set. And these are similar pictures of dogs, but it's in a more common context. So you have stuff around it, better for training. So the data set has, a lot of images, 300,000. They've labeled about 90 different classes of objects in there. So it's a pretty common data set to be used for object detection. We're using the bounding boxes to help build the image classifier. But this is pretty common in the machine vision world. So the TensorFlow Lite Micro comes with a great example for building your own vision sensor. This one is a person detector, and I put together a little board. I have my Arduino on there and my ArduCam. And the model that comes with this example was trained using the visual wake word data set. And so I put this together, got it running, and it worked surprisingly well, shockingly well for something that being powered with a very small battery. So I was both impressed and encouraged, which led me to the next step of the journey is, how can I grow this? How can I make this better? So as part of the tutorial on how to do person detection, it includes sort of the following pros of, there's all these other classes of objects. Why don't you go try to build and customize one for a different type of object besides person? And it comes with a number of scripts for building your own data sets using the visual wake word scripts. So, went ahead, did that. The training does take a bit of time. It does, as opposed to doing any sort of transfer learning, it does a full training of the model from, randomized weights. So, it takes about 24 hours or so with some beefy GPUs working. I had a bit of some unexpected results. And unlike person detection, when I tried working with different classes of objects, the results were just didn't perform as well as I expected. So when I trained this in Jupyter Notebooks, and I saved some of the Coco images and tried just running those through and testing against the model just on the computer, it worked pretty reliably. However, when I loaded it up and brought it out into the real world, I found that the performance was pretty erratic. There were, cases where, it could easily get 90% performance, but then slight variations in perspective caused a very big drop in the confidence. Different types of objects. So, it could be, and here's an example of apples. Different colorations in the apples had a big effect on performance. Different sensors, image sensors, if the image was coming from a nice, if I took the image, using a camera phone versus using the ArduCam camera, that really affected performance too. Another interesting thing was that if you weren't paying attention, a lot of these blind spots ended up getting averaged away when you started looking at the confidence matrix. So in the confidence matrix, it would really average away the fact that certain aspects of a car reliably fail, which was really, to me, spoke to the value of going and making sure you're testing these things in the real world and evaluating at a more granular scale some of the performance you're getting versus simply doing this in Jupyter notebooks, getting your performance results and then assuming this will work well on a sensor deployed into the real world. So from these sort of initial unpredictable results, me and my co-conspirator wanted to dig into this a little bit and try to get some ground truth on what was causing this and why this may be happening. So one of the first things, one of the most likely suspects is that the different class of objects that are labeled inside the Coco data set is very uneven. There are a lot more example images or labeled bounding boxes of persons. You sort of get a very dramatic and long tail fall off on the number of other objects that are available in the data set. So we sort of were looking at objects spread across this distribution. We trained models for cars, dogs, bicycles, and apples. And with these, we found similar failings where it would work really well for certain cars or certain perspectives of cars, but it would reliably fail on other types of cars or different perspectives. Again, it liked certain types of apples much better than other types of apples. Probably because there's just not many different example images inside the data set that we were training against of these different types of objects. So there was not much variation in perspective or the types of objects. So, when you think about this a little bit more, it does make sense if you go, back down to where the images in the Coco data set came from. These photos were all taken by photographers and intentionally placed onto Flickr. Since they were taken by photographers, they were from a perspective of a photographer. And that may not be the same as what the sensor may be seeing. So if you have a sensor mounted, 90 or 45-degree angle looking down at a car, that's not an angle that might be common for a photographer to take a photo of a car. So you're getting a very different perspective for the image sensor. Another one we definitely noticed was, most of the Flickr images are intentionally composed, so the car is in the right position. But you don't always have that luxury with a visual sensor because it will just at periodic increments take a photo. Cars may not be correctly positioned or aligned in that photo. It may only catch part of a car just because they're driving by. And finally, all of the images were intentionally uploaded to Flickr. Usually these are the nicest photos that a photographer takes, not the misshapen bad ones. And that's often what you get from the visual sensor. So playing, I was talking with sort of different examples of photos taken of a car as we walked around and desampled down to the input resolution for the model. And you can see it really likes the sides of cars, not so much the front and back of the cars. Sort of summarize that, vision sensors are not cameras. And similarly, the photos taken from the internet aren't necessarily what a vision sensor may see. Again, not from a photographer's perspective. The vision sensor, these cameras will have lower quality images. The white balance may be off. They may be washed out. And again, since you're taking photos at a periodic instance, the composition may be very awkward. You may only have partial crops of a person. To sum it up, Instagram isn't real life. photos from the internet may not be the best training data for vision sensors. So sort of the lessons learned on this were to carefully evaluate model performance in the real world. It's great that you can get this, based upon, you can, write a paper based upon how much you're able to compress a model and make it work within performance bounds, but really being able to evaluate how it performs in the real world is really important. I still think the visual wake word data set's really important. It's a great way to bootstrap a model and to get something started. It's then really easy to use that initial model to capture samples with the actual sensor you're using, and then augment your data set with the images it's just not sure what they are. Finally, using image augmentation is really important. And it's a step that's sort of left out of the visual wake word training script, where I think you could do a lot more to help simulate the poor quality you may be getting from the image sensors on these devices. And also to help maybe handle where you might have part of an object partially obscured or cut off just because of the periodic nature of how the images are taken. One of the final things there is also just remember that the input tensors into a lot of these models are very small. So you actually should be making sure the objects you're going to be focusing on will be large enough to identify, when you actually look to place these sensors in the real world. But overall, it's very promising. With the right data being collected, I think these will be a very powerful way to start gathering more data from the real world. So I'm very interested in working with other people and seeing if we could start building some image data sets specifically designed for sensors that might better capture what they would be seeing, so we can do some more and better real world evaluation as we start to do benchmarking. So I'll turn, and that's the end of my talk, so I'll just turn this back over. See if there's any questions.
So Luke, I actually had a question. So you looked at the number of labels of the different images in the database. Was there any correlation between the quantity in the database and the confidence level? Obviously, for people, it did really well, but did cars do better than apples because there were more cars than apples?
Yes, so I do think we saw that sort of similar fall off on how well it worked, but it was where I saw it was more on you could still have very high confidence models for predicting apples, but it was more sensitive to variations in the types of apples and the perspective, whereas the car model was a lot more robust. It was susceptible to certain models it just did not like, but overall it was more robust to variations in the types of cars and a little bit more on the perspective. Whereas with apples, it wanted sort of the canonical apple in a fruit basket in a very typical setting. It started to be more sensitive to the top-down view of an apple or apples that were a bit more red. And I guess one of the things I'd probably add in too is transfer learning is great. So, use this to get started, collect things, especially as you get sure of, how your model and your visual sensor will be used in the real world. Collect those images, use transfer learning to help bolster the areas where the model is not sure or giving you incorrect answers. And you really take an iterative approach to developing the overall data set you're going to be using and training against for these real world deployments. So it sort of ends up being one of those things where you're never really done until there's always more data that can be collected and help improve your accuracy in the real world. So think of it as a journey versus once you finish completing training, you're done and good to go.
Thank you.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs, DSP Group, Edge Impulse, EMSA, Gray Matter Labs, Greenwaves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SenseML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsets.